Hello, everybody. Welcome back. It's Professor Reitz, and this is our second lesson with distance learning. I hope everybody is doing well and staying healthy. I'm going to try something. This is the third time that I've tried to record this video. This time, I'm going to try to move quickly and not talk so much, but I'm not sure if that's actually something that will be helpful or not. So, you guys are going to have to let me know. Here we go. We're introducing a new topic, logarithmic and exponential functions. We're going to start with exponential functions. These functions are sort of the next logical thing to look at after we look at polynomials, which are sort of the building block functions, as we've discussed. And what is an exponential function? Well, it's a function that looks like this one, f of x equal 2 to the power x. And you'll notice that there is here, still, as in the case of polynomials, we're raising something to a power. We call that number 2 that's down in the base, we call that the base. And we call the x the exponent. It's just whenever we talk about powers. And in polynomials, the variable, the x, is down in the base. In exponential functions, the x is up in the exponent. Okay. The only other thing that we might have in an exponential function is we might have a number multiplied in the front, a little bit like a coefficient in a polynomial. And so what we're going to try to see is the following questions. What happens when we change the base? What if we look at different bases? And then what happens if we look at different numbers in the front, different constants in the front? And in particular, when I say what happens, I mean we want to look at the graph. And we want to talk in the graph about the domain, the range, any asymptotes, and any intercepts. So we're going to go back, we're going to look at the graphs of a bunch of these, and then we're going to come back here and fill in what we've learned about those items. Here we go. So I want to start by looking at the function 2 to the x. You'll see this is the one that appears in black on the screen. Let me get myself a little pointer. So it appears here in black on the screen, and you'll notice that it's the only function on the left-hand side in the list of functions that's lit up. When we think about plugging different numbers into 2 to the x, well, if we plug in the number 1, x equal 1, into 2 to the x, that becomes 2 to the 1 power, which is equal to 2. So this is the point 1 comma 2. And as we plug in bigger and bigger numbers for x, what we see is that the answer we get for the output, 2 to the power x, gets larger very fast. So for example, when we plug in the number 4 for x, we're going to have an answer of 2 to the 4, which is 2 times 2 is 4 times 2 is 8 times 2 is 16. 16 is all the way off the top. This thing only goes up to 8 in its scale here. So that's, you'll see it's already off the top of the graph when we try to plug in the number 4. When we try to plug in the number 0 into this function, we get 2 to the power 0. And anything to the power 0 except 0 to the 0. That one was not allowed. But any other number to the power 0 is just equal to 1. So when we plug in 0, we get an output of 1. And when we plug in negative numbers here, we need to be aware of the rule for raising things to negative powers. If we take the number 2 and raise it to the power negative 2, the effect that that negative exponent has is to flip the whole thing to the bottom of a fraction. So instead of 2 to the negative 2, we think of it as 1 over 2 squared, which is 1/4. And 1/4 is a positive number, but not a very big positive number. If we go, and that's why we see for x equal negative 2, we get a y that is a little bit above the x-axis. It's a little bit positive, but not very far above. And as we make that power bigger in the negative direction down here, what happens is that we get 1 over a larger and larger number, which means that we're going to get closer and closer to the x-axis. Okay, that is 2 to the x. Next, we want to look at what happens when we change to a different base. So let's look at the function 3 to the x. Here, this one is in red, and you'll see compared with the original 2 to the x, 3 to the x curves up more sharply on the right. That's no surprise, because when you take 3 and raise it to a power and compare raising 2 to a power, you expect 3 to the power to be bigger. And that is a correct intuition as long as the numbers you're plugging in are positive numbers. This red line, 3 to the x, sits over the black line, 2 to the x. It's interesting that it switches on the negative side, so 3 to a negative power ends up being smaller but positive, but smaller than 2 to that same negative power. For example, if we plug the number negative 2 into the function 2 to the x, we get 1 over 4. If we plug the number negative 2 into the function 3 to the x, we get 1 over 9, which is closer to 0 here. And so what you observe is that for the function 3 to the x, it is similar to 2 to the x, but for positive x's, it's above. And for negative x's, it lies below. We say that it grows more quickly, and it also approaches 0 more quickly. Okay. The next one that we're going to look at is just what happens when we increase the base to 10. And what you'll see, is, maybe as you expect, this is the blue line, is that it curves up even more steeply on the right, and it curves down towards the x-axis even more steeply, more quickly on the left. Now, all three of these share a point in common, which is the point where x is 0. And when x is 0, if you plug 0 into any of these three equations, 2 to the x, 3 to the x, or 10 to the x, what you're going to get is a number raised to the power 0, and that is always equal to 1. So anything to the 0 power is 1. There is an exception. We're not allowed to take 0 to the 0 power. But aside from that, we get 1, which means that these are all going to have a same point in common. When you use an input of 0, the output is going to be this number, 1. Okay. So let's just recap what we've learned so far. The domain, if you remember, you were allowed to plug in any real number that you wanted, which means that the domain, well, we could look at it as from minus infinity to infinity, or another way to say that would be all real numbers are. The range, however, when you take a number like 2 and raise it to a power, you never get a negative answer. You can plug negative numbers in for x, but the effect that that negative has is to turn it into a fraction and give you a very small number as an output. So the range never gets negative. The range is only positive numbers. And in fact, you can't get 0 as an answer either, which means that the range is 0, infinity. It's only the positive real numbers. Asymptotes, all of these had an asymptote as you were going off to the left. It was a horizontal asymptote. Those things were approaching y equals 0. And the intercepts, they all had a single y-intercept, and that was the point 0, 1. This is the one point that they all share in common. Okay. Now let's look, we've seen almost but not quite all of what can happen when we change the base. So, let's consider what we do. We said, so it's a rule for exponential functions that the base has to be positive. Why is that? There's a really good reason for it, and we'll see that maybe a little bit later on. So if the base is positive, look, we've looked at bases 2 and 3 and 10, but also there's something interesting and a little different that happens when we use a base that is less than 1, but still positive, like a fraction, like 1/2. So 1/2 to the x, this is what the graph looks like. This one is in green, and you'll notice that it's kind of similar to 2 to the x, but it's almost like a mirror image. It goes up on the left-hand side and down on the right-hand side. And that's because 1/2, when you raise it to a high power, a positive power, then you just get 1/2 to a power becomes a very small positive number. So you see that behavior of approaching 0 on the right now. And when you plug a negative power into 1/2 to the x, what you're going to end up with is the exponent flips that thing over, which turns it from a fraction 1/2 into 2 over 1, into just a nice whole number 2, something that's going to get big. And so on the negative side, this one now grows and goes towards infinity. Let's look at one more. Let's make our base, this was a base of a half. Let's make our base even smaller, closer to 0. Let's do 1/10. So the base, sorry, the exponential function 1/10 to the x, it does behave similar to 1/2 to the x. That is, it goes up to the left, and on the right-hand side, it goes down and approaches the x-axis. You'll notice that by making the base smaller, comparing 1/10 to the x with 1/2 to the x, when we make the base smaller, we make it curve up faster, and we make it go down towards the x-axis faster. So it does both things more quickly. Its behavior changes quicker in both directions. So this means that over here, the 1/10 to the x is going to be below 1/2 to the x, and over here, 1/10 to the x is going to be above 1/2 to the x. However, other than that, these functions where the base is between 0 and 1, they look very much like exponential functions, the original exponential functions we looked at, but they're sort of a left-right mirror image. They go towards an asymptote on the right, and they go up on the left. They're just as if you put a mirror right on the y-axis and then reflected one of the original graphs over, you would get this one. Okay. So, in fact, what's nice is that the domain goes from minus infinity to infinity. The range is still positive numbers. The asymptotes are still y equals 0, and the intercepts are still 0, 1. And that is true for any base bigger than 0.